Alright, so we're group 15, and this week we did lessons 10 and 11. And going through our group meeting quizzes, we got, starting on question 3 of lesson 10, we got 16.45, because the margin of error for 90% would be 1.645, and you take that number and multiply it by your standard deviation divided by the square root of your sample. So you get 16.45. In question 4, the following statement is true, that the mean of your sample is a point estimator of the mean of the population. Because we don't know the true mean of the population and we can take samples, we want that to be close to it. So question 5. Using the data provided above, what is the point estimate for the true GMAT score? And so, using the information from question 4, where the sample mean is a point as an indicator of the population mean, it would be 526. For question 6, what is the margin of error for the 95% confidence interval of this score? And that would be 27.685, because 0.95 in the probability applet would be 1.96. And so 1.96 times 113 divided by the square root of 64 gives us 27.685. So what is the lower limit of this confidence interval? So what we do to find this is we take the sample mean plus or minus our margin of error. And so our sample mean for this problem was 526. So 526 minus 27.685 gives us an answer of 498.315. And what is the upper limit of this confidence interval? That we just take the mean and add our margin of error, and we get 553.685. So what would happen to the width of the confidence interval if we increase the sample size? Well, if you increase the sample size, the margin error is going to decrease because it's hopefully going to be closer to the population's mean. So what would happen if we changed the confidence interval to 99%? Well, our margin of error would increase because we're trying to say within 99% of the data, the true mean of the population lies. So it's wider than narrower. So in question 11 is a bright light bulb company is planning a case study to assess the average lifespan of their light bulbs. They know the standard deviation is 400 hours, and they want a 95 confidence interval with a margin of error of 50 hours. So we put in our same formula that we've been using, except now we know the margin of error is 50. So 50 equals 1.960 times 400 divided by the square root of unknown. And so when we solve that algebraically, we get 246, because we round up to the nearest whole number. It's 245 point something, but you always round up in a population, or in the sample size. So it would be 246. So the mean salary of actuaries is the population is $100,000, and the standard deviation is 36,730. And we're interested to know if the mean salary for women actuaries is different from the population mean. But we're not sure if it's higher or lower, so we set up a hypothesis test with a significance level of 0.05. And we have our two statements there, our null hypothesis and our alternate hypothesis. And so our sample size is 36, and our mean is $111,000. So what is the lower limit of this confidence interval? So first we find the margin of error, which again, we take 1.96 multiplied by our standard deviation of 36,730 divided by the square root of our sample size of 36. And then we say that our confidence interval is the sample mean plus or minus the margin of error. And so when we subtract our margin of error from our mean, we get $99,002. And what is the upper limit? And we get $122,999. And then finally, question 14. There are 3 requirements that need to be checked when computing interval for a mean. And they are: a simple random sample was drawn from the population, the standard deviation is known, and the population, or the sample mean, is normally distributed. And that's it for lesson 10.
Could we actually real quick go back to 12 and 13?
Of course.
I'm just confused finding the lower limit and the upper limit.
So they're talking about the margin of error. And so first you find the margin of error for this problem. So to find margin of error, it would be the 95% confidence interval, which would give us a z-score of 1.96. And so we do 1.96 times our standard deviation of 36,730 divided by the square root of our sample size, which is 36. And then to find the lower level, we do our sample mean of $111,000 subtracted by our margin of error, and that gives us the lower limit. And then the upper limit.
We subtract the margin of error.
Yeah.
To find the lower, and then we add the margin of error to find the upper limit.
Exactly.
Oh, okay. And then the margin of error is half of the confidence interval, right?
Right.
Okay.
Yeah. It's like the standard deviation for confidence.
Okay.
Yeah. Any other questions in this lesson?
Nope.
All right. So we'll go to lesson 11 then, which was, okay, so lesson 10 was if we knew the standard deviation, if we knew sigma. Now this one's saying, normally we don't know what the standard deviation is, and so how do we find out how to get it? And the important part of this lesson was you can't set up the formula to use the variable of standard deviation because we don't know it, we can't be exact. And so we have to base it off of our sample size. And so we replace our variables with t and s. Our t is S is our standard deviation, and t-score would be our curve. And our curve shape is closer to a normal curve the larger our sample is. So you really want a large sample in order to get a basic curve and find a proper standard deviation. And so for question 3, it says, in previous lessons we had assumed that the population of standard deviation, sigma, was known. In this lesson, we're making a different assumption about it. What has changed? So in this one, we assume that sigma, or standard deviation, is not known. We don't know what it is. And so for the next 2 questions, they give us this null hypothesis of the population mean is 8, and the alternate is the actual mean is greater than 8. Assume that the standard deviation isn't known, and your sample size is 9. Your sample mean is 11, and you find an S of 6. So our S is our test value. So we don't know the sigma. So we say no. But what is our value of t? Well, we find t by taking the sample mean subtracted by our population mean. So 11 minus 8, which is 3, and divide that by our S value of 6 divided by the square root of 9, or 3. So we get 3 divided by 2, which is, of course, 1.5 for our t value. So use the following values which are pulled and copy and paste them in your software. I used SPSS for this because it was just really simple. It did all the work for me. But you can't copy and paste because it's iLearn. So you have to be careful. There's 20 variables here. So if you type all 20 of them out right, you'll get the right answer. Which you go into, once you put in your variables, you go to Analyze, Compute, and then say compute mean, and then one sample test of t. And so what that tells you is that the population mean, the sample size mean is 98.22. and then you find the standard deviation, or S value, not the actual standard deviation, but the calculated one, as 0.921. And the t-score is in the bottom left corner of that data, and that would be negative 1.843. And then the p-value is actually, in SPSS they call it the sigma with double tail. And for this one it's 0.04. And that's our p-value. So we set
What did you get for that again?
So our p-value is the double-tailed sigma in the data.
Yeah.
That comes up. So I got 0.04 for that.
Okay.
And 0.04 is less than 0.05, which is our level of significance. So we reject the null hypothesis because it's too small. And so the next several questions are the same thing, except it's using what is it? The baby boom births at hospital. Minutes between births at hospital. And there's 21 values in this one. So you have to be careful because there's 21 values. And if you mess up one, then you mess up all of your data. And you can't copy and paste, so you really have to make sure you get the data down right. And so when you type all of that in, and you highlight it and say analyze, and then test the mean to 1t, you put in your variables, and you put in your test value as your hypothesis of 40. And you get the p-value of 0.995. And again, that's under your double-tailed sigma. So it's 0.995. And so we set our significance level to 0.01, and 0.995 is larger. So we fail to reject the null hypothesis. We assume it's true. And so you decide to try another alternative hypothesis, and this time you use that it's less than 40 for the actual. And so, did the p-value increase or decrease when you do this? Well, it would decrease when you do that, because before your hypothesis was it was not equal to 40, and so your p-value is trying to determine everything. But when you use greater than or less than, you divide that double-tailed sigma value by 2, and so it would decrease. So when you take 0.995 divided by 2, you get 0.45 something. And so, again, that's larger than 0.01, so we still fail to reject the null hypothesis. And then questions 14 and 15 are constructing a confidence interval for this data. And so you take your sample size mean, which you calculate in there, and you subtract it from your margin of error. And you get 23.5, or 23.5 for the lower limit. And when you add it, or you take your sample size mean and add the margin of error, you get 56.5. And again, you find that by running that data in through SPSS or that special Excel that's on their Wikipedia. I just think SPSS is easier. And you just take that data and plug it into your equation. Again, the equation is T equals the sample size mean minus the population mean divided by your S value, which is also divided by the square root of your sample size. Does that make sense?
Yep.
All right. Do we got any questions?
What was
Yeah.
6?
For 6?
Yeah.
For 6, I got 98.22 as the mean. So, any other questions?
Nope.
All right. Cool. Well, thanks, guys, and we'll see you next week, right?